All right, in this section, we're going to be talking about equations of lines and planes. This is section 12.5. Now, to draw a line in 3 space, we need 2 things, a point on the line and a vector giving the direction of the line. So basically, draw a quick dotted line here. This is our line, and I need a point on the line. So there's my point. And we need a vector, so let's just draw a vector here. And that's giving the direction. Now let's start again. I'm going to draw another little line here. This time we're going to put more information on it. I'll call that line L. So I need a point on the line again. So here's my point. And I need a vector. There we go, pointing in the direction we want along the line. So here's my point. And that's the starting point of the vector, the initial point. So to indicate that, I'm going to put sub-zeros on x, y, and z. And this is my vector v. And just generically, I'm going to call the components a, b, and c here. And this gives me my direction. Now, take any other point, say we put a point here on the line, and I'm going to call that x, y, and z. Now to represent this vector, we can come up with, let's see, a larger vector here. Let me just draw this. I'm going to start at the initial point again, and I'm drawing along the initial vector, and I'm going to go all the way up to the point that we just drew, x, y, and z. Now, this vector that we just drew, we can always come up with the components by writing, taking final minus initial. So the vector here, I could take the x minus x naught, y minus y naught, and finally z minus z naught. So we have 2 vectors here. We have the vector v that we started with, that's over here, and we have this new vector that we just drew, and they're both pointing in the same direction. Let me erase my arrows here off of the diagram, and let's go to the next. Now we said that vectors v and the x minus x naught vectors are parallel, or pointing in the same direction, so we can say vectors v and this one, x minus x naught, y minus y naught, and finally z minus z naught. Well, we can think of them as being scalar multiples of each other. So we can start with x minus x naught, y minus y naught, z minus z naught, and that's equal to a scalar multiple of v. So I can take t as my scalar times my vector v. My vector v, I can replace the t, or the v, with its components, a, b, c. And then we can even multiply the t in, and I'm going to write these in alphabetical order. So the first element is at, then, hey, how about b? bt, that'll be correct, and then finally ct. And we know that the only way for 2 vectors to be equal to each other is when the components are equal. So it must be that x minus x naught is equal to at. So let's write x minus x naught is equal to at. And then y minus y naught must be equal to bt. Y minus y naught is bt. And finally, z minus z naught is equal to ct. Z minus z naught is ct. Or, if we continue, I'm going to just rearrange these equations. I'm going to write x equals, and put the x naught on the other side, plus at, and then y is equal to y naught plus bt, and then z is equal to z naught plus ct. So we can see that an equation of a line in 3 space can be given by a set of equations. We have 3 equations here. That's our set of equations. These equations are called parametric equations. And let's even state this. We'll put, let's see, all points, x, y, z on the line will satisfy the set of parametric equations. Okay, here let's determine parametric equations of the line that passes through the point 3, 2, -1 and is parallel to the vector I minus 2j plus 3k. So let's write up our solution. First, we need a particular point on the line. Well, the point on the line, we can take what's given to us. We can use the 3, 2, -1 point, and we can let that be our initial point, like the x naught, y naught, z naught representation. Next, we need a vector that's parallel to the line. So we need a vector, I'll call it v, is equal to, well, I'm going to use the vector that they gave us because it says parallel to, so I'll write it in the notation. Instead of the ijk, I'll write it as 1, -2, and then 3. So there's my vector v, and all I have to do is plug into the previous formulas. So what I mean by that is x is equal to, remember it was x naught plus at, y is equal to y naught plus bt, and then z is z naught plus ct, which is equal to, let's see, we have a 3 is the x naught point, plus 1t, I'll just write as t, and then we have a 2 is the y naught, and then we have plus a minus 2, so let's just write minus t, 2t, excuse me, and then we have a -1 plus 3t. So here we have a set of parametric equations that describe this line. And what you're going to notice is that this is there's multiple answers. So notice if we let t be equal to 0, then we get to 0.32 -1. But t could be 1. If t is 1, what do we get when we do the arithmetic? We get what? 402 is another point. And we can let t vary throughout the reals. So you can see there's many different ways to represent this using parametric equations. Okay, next, there's other ways we can represent the equation of a line. Here we're going to do the vector, or talk about the vector equation of a line. So first of all, let's review what a position vector is. Suppose we have the coordinates x, y, z in 3 space. There's x, there's y, and z. And remember, the origin would be 0, 0, 0. And suppose we have a position vector. The position vectors start at the origin and goes up like this. We'll call that, say it points to that point right there, and we'll call that point x, y, z. And this is my position vector. And it's common to call this position vector, at least in our book, lowercase r. So that's what we'll call it r. Now what's nice about a position vector is when I take the final minus initial, it's always the final minus 0. So it's pretty easy. The components of the position vector are just the same as the point, except that it would use vector notation. So we get x minus 0, which is x, y minus 0, and z minus 0. So we get x, y, z. And why don't we just put the r in front of it here? There's the vector, and we'll write it like that. And what we see here, this position vector r, it's pointing, in a sense, pointing out the position of x, y, and z, x, y, z, that point in 3 space. It's pointing in that direction. All right, to continue developing this vector equation of a line, here we have the coordinate axes drawn in 3 space. And suppose we have a line. I'm just going to draw a line that's existing in 3 space here. And let me try to draw a better line than that for us. There we go. So there's our line. and we'll just call it L, again, for line. Now our position vector would start at the origin, and it's going to point to a point in space on that line. So there we go. Let's call this R for position vector, but since it's our first one, we're going to call it R sub 0. And that gives us x0, y0, and z0. Now we're going to draw another vector, v. It's going to start where r ends. So it's going to start right here at where r ends, and it's going to go along this way here. And that's my vector v, and it will have components a, b, c. I'll put a little hat on v there. So that's telling us the direction of the line. The vector is going in the direction of this line. It's parallel to the line. Now, if I want to go 2v, then we could just continue this here, and that would be 2v in the direction of the line, and we could do 3v and so forth. We could even go in the opposite direction. We could start at v again, where we first started, and go about negative v, or negative 1v, in that direction, and we could keep going in the other direction. So we could trace out the entire line by that. And the way that we're going to represent this with these vectors R is, okay, if we continue, I want to draw or come up with a representation of this line using this notation and this new concept here. So the position vector R naught starts at the origin and points to where the vector V starts, and then the V vectors, or the multiples of V's, go along the line. So if we know how to add vectors, we go from the beginning of R naught and we end at the end of R naught, and then V starts. So if we do that, we could represent this vector that I'm drawing here as well. It's simply the vector R naught plus the vector V, like that. And, well, we have that 2V. We could do R naught plus 2V, and we end up here. So here's R naught again plus 2V, and we could continue that. We could even go in the opposite direction. We could do the negative R naught plus the negative V, and so forth. And what we're going to get, I'll just write this underneath here and make some room. We're going to have this right here, R naught plus V. We could take R naught, what we drew was R naught plus 2V. We could do R naught plus 3V, and so forth. And we even could take R naught in the other direction plus a negative 1V, or we just write it as minus V, and continue forever, and we'll generate the line. And what happens is t can be any real number. So if we let t vary through the reals, we're going to generate the line R. So what happens is we are going to get R, just the R notation, no subscript. Now this is going to be equal to the vector R naught plus, now t can be any scalar, t times the vector v. And this is what we call the vector equation, or the general vector equation of the line. All right, so let's find the vector equation for the line that passes through the point 513 and is parallel to the vector I plus 4j minus 2k. So let's begin this here. I'm going to start with the R naught vector. I'm going to use the point, the position vector that points to 513 is a good place to start here. And my vector v, I'm going to use the other notation, the 1, 4, negative 2, between the vector brackets. So the vector equation is going to be R equals R naught plus TV, which equals 5, 1, 3, that vector, plus t is the scalar in front of 1, 4, negative 2. From here, it's just combining these vectors, and we'll multiply the t in, or the scalar in, add the vectors, and we end up with, finally, 5 plus 1t and then we have 1 plus 4t, and then 3 minus 2t. There we go. We're going to talk about another way to represent lines in 3-space, and I'm going to begin with parametric equations. And we talked about this just a few minutes ago. We can write x equals x naught plus at, y equals y naught plus bt, and then z is z naught plus ct. And what we can do is, I'm going to solve each of these equations for t. So the top equation, x equals x naught plus at, becomes t is equal to x minus x naught all over a. And then we can write the second equation similarly. It's going to be y minus y naught all over b. And then the third one is z minus z naught all over c. Now, if we set these equal to each other, they are what we call the symmetric equations of the lines. Symmetric equations of the line. And let's write x minus x naught over a is equal to y minus y naught over b equals z minus z naught to z naught. There we go, over c. All right, let's talk about equations of a plane. Here we start with a plane in 3-space, and let's put a point on the plane, and we'll call that x naught, y naught, z naught. And there's a vector. Let's put a vector in the plane here, so parallel to the plane, and it's pointing to the point, say, x, y, z. Now, if we take a perpendicular vector, a vector that's perpendicular to the plane that goes right through x naught, y naught, z naught. We can draw it like this. Let's do the little perpendicular symbol here. And then I'm going to call this vector lowercase n and define it to be a, b, c. Now, let's make some room here. Now this vector, ABC, is perpendicular to any vector in the plane. So A, B, C, perpendicular to any vector in the plane. So ABC, we called it n, so I'm going to put n here, and I'm going to dot it with r minus r naught. Comma. And that's going to be equal to, well, if I dot these two vectors together, it's going to give me 0. And I can rearrange this simply by writing n dot r is equal to n dot r naught. And this is what we call vector equation of the plane. There we go. Now what we could do is just expand on this a little bit. Let's replace the n with the ABC again. And then we have a dot. And then the r minus r naught. Let's replace that with x minus x naught, y minus y naught, z minus z naught. And that's still going to be equal to 0. So if we dot these together, we're going to get a x minus x naught plus b y minus y naught plus c z minus z naught, and that's still equal to 0. This is what we call the scalar equation of a plane, of the plane. Okay, in this example, we want to find the equation of the plane through the point 4, 0, negative 3, and that has normal vector j plus 2k. Now the reason we called that normal vector, or that vector ABC, lowercase n, is because it stands for normal vector, lowercase n. So we are going to use, let's use this equation, a x minus x naught plus b y minus y naught plus c, z minus z naught, and this is going to be equal to 0. We know that. Now n is going to be the j plus 2k. Okay. Equal, I'm going to write this j plus 2k, but let's put it like this. 0i, 1j, 2k. And remember that is the ABC. And the point, so let's say point, x naught, y naught, z naught is 4, 0, negative 3. So this is going to give us a is 0. I mean, we don't have to write this, but I'll put it in for the example here. And then plus, we don't have to write the 1, but it'll serve the example. And then plus 2z plus 3 still equals 0. Make some more room here. Now all of this is equal to 0. And we get 1 times y plus 2z plus 6 is equal to 0. And there we have the equation of the plane. All right, what we're going to do for this video here for section 12.5, we are about 2/3 of the way through everything I wanted to complete, and I think that is going to be enough for us for this video, including we have the other video for section 12.4. So we're going to stop here, and we'll continue any other topics in section 12.5 on equations of lines and planes. We'll do that together in class. So thank you, and I will see you all in class.